Okay, hi there, Dr. Matthew J. Trom here. We are still in Module 4, Transient Conduction, and we are going to do Lecture 10, which is Combined Spatial and Transient Conduction. This corresponds to a couple more sections in Chapter 5. So here's the corresponding reading. So 5.4, Spatial Effects, 5.5. Plane wall with convection, 5.6 radial systems with convection, and then two appendix sections. So 5S1, which is graphical representation of 1D transient conduction, and then 5S2, which is analytical solution for multidimensional effects. If you are looking for the ADA compliant transcription, this is the video that will generate that transcript. So I don't have the transcript yet, but once the video is done and I get the AI transcription, there will be a link here that you can click on, and that will take you to the Zoom channel that has the transcription in it for those who are looking for it. Okay, so let's get started. Let me get my laser pointer. There we go. All right. So as you will see, this section is well, it's a lot. And actually, this is one of my favorite sections of heat transfer because it illustrates just how powerful and how useful some of these techniques are. The fascinating thing is a lot of this stuff was developed before there were any computers, any real computational power. And so all of these solutions are like closed form analytical solutions that were all developed basically for calculation by hand. Now, in 2026 or whenever you're watching this, that might seem, sort of silly. We have all this computational power today. We have AI. So, why bother with all these techniques? The reason that these techniques are so important is because you need a way to test and verify and check to make sure that, what you got out of the AI is correct, or what you got out of particularly CFD or FEA, finite element analysis, or computational fluid dynamics. A lot of times, students, even practicing engineers, will just go to those software packages to try to solve problems that actually already have solutions. So there's no need. But a good way to check to make sure that your FEA or CFD is functioning correctly is to check it against the exact solutions which you can get from these techniques. But as you will see, it gets to be an awful lot, and so this meme kind of stuck out to me when the heat transfer is just a little too much. And so you'll see this image again when we get to the point in the kind of mathematical analysis where we've reached that point of saturation, and then I'll show you some kind of shortcuts that you can use to get solutions that are almost as good as the exact solutions, but don't require nearly as much computation. So anyway, we'll see Frodo again. Okay, so you guys have seen this slide before. This is my AI generated slide, right? So here's my Terminator up at the top. I fed my slide deck to AI and I said, critique this for me, roast me. And the AI is like, you have to start with this slide. So I've already gone through this, so I won't do it again. But just suffice it to say that this lecture is about blocks number 2 here, which is spatial and temporal gradients that we're basically solving simultaneously. Okay. All right. So you guys have seen this already. This is just a refresher. So remember like where we came from, right? So we started over here with lumped capacitance. And so lumped capacitance is the idea that the entire body that you are heating or cooling basically maintains constant temperature all the way throughout, constant spatial temperature all the way throughout as the temperature is changing with time. And so we walk through kind of the first law analysis. We get to this expression for the energy balance. So the heat leaving is equal to the change in internal energy. We have from thermo an expression for the change in internal energy. We use our law of conservation of chalk, which is my joke from when I was an undergrad, and my chemistry teacher described that as just a way of writing things more succinctly to define this thing called theta. which is just a temperature difference. Note that the derivative of theta with respect to time is also the derivative of temperature with respect to time. That's this line. And so we're able to convert this expression of the first law into this expression, which can then be integrated. And we get this equation, which we can then kind of manipulate to get temperature as a function of both the Biot number and the Fourier number. So Biot number gives you a sense of like the spatial temperature gradient inside the object versus the temperature gradient right at the boundary, right? So it's like conduction versus convection effects. And then the Fourier number, which is like a dimensionless time. So that temperature is what you're trying to solve, and then minus ambient temperature divided by the initial temperature of the whole body minus ambient temperature. So that's a dimensionless temperature ratio, and then that's just equal to E raised to the minus Biot number times Fourier number. And just as a reminder, the Fourier number is alpha t over LC squared. LC is some characteristic length. For a slab or a plain wall, it's like half the length of the wall, the length to the inside of the wall. For a cylinder, it's the radius of the cylinder. For a sphere, it's the radius of the sphere, and so forth. And so this is all true and correct, and very easy to implement, provided the Biot number is less than 0.1. And I say if Biot number, which is HL over K, is less than 0.1, then the lump capacitance error is small, for an engineering perspective. And that means you can use this, right? So basically what this means, if it's small, is that K is much bigger than H times LC. And so what that means is that because K is the thermal conductance is so big, any sort of temperature gradient that you have inside the object is going to be eliminated, because the heat is just going to conduct all the way through and wipe out any temperature gradient that might exist, because K is so big. And so that's fine, except when you run into a situation where this is not true. So what happens? So I say down here, what do you do if the Biot number is larger than 0.1 and this lump capacitance approach is not valid? So that's what this lecture is basically about, is what to do when the Biot number is greater than 0.1, which happens quite often, actually. Lump capacitance really only works for specific situations when you're dealing with relatively small and highly conductive bodies, so like little chunks of metal and stuff. So anyway, what do we do? Okay, so we got to go all the way back. So remember, like the first lecture that I ever gave in the class was about the heat equation. So we're going to go all the way back to the heat equation, and remember that the heat equation has these spatial temperature components, and it also has this time-based temperature component. And if we don't have any internal energy generation, we get this. Oh, hang on. Nope, it's here. We get this version of the equation, which is the Fokker-Planck diffusion equation, which, if you write it just in compact form, is just del squared T, right? So second derivative with respect to spatial dimensions equal to 1 over thermal diffusivity times the first derivative of temperature with respect to time. And that solution looks something like this. As time progresses forward, this peak will drop, and it will sort of even out here towards the edges. And so it's this equation that we are interested in solving for situations where the Biot number is greater than 0.1, right? So we're going to go all the way back to basics and solve this guy. Okay, so for this section of the book, for the most part, we're just concerned with spatial one-dimensional temperature profiles. So this is an AI generated slide, and this just shows that same equation that I had before, right? This one, except in terms of just one spatial direction instead of 3 spatial directions. And this is basically just the diffusion equation, right? So if you have a concentration of thermal energy over time, that concentration of thermal energy is going to diffuse outwards, dissipate outwards through the object. And just like mass diffusion, right? Just like in chemistry, if you have a highly concentrated chemical and you drop it into water, it'll diffuse outwards following the exact same equation. Right. So same principle. And you guys have seen this before. This was in the introductory slides to the course. Um, okay. So you guys have seen this as well, right? So here's the heat diffusion equation in one dimension. So this is just to point out where we started, which was the overall three-dimensional heat equation. And then we're going to imagine, right, that heat transfer only happens in one spatial direction. So anything with respect to X, anything with respect to Y goes away. And we've, sorry, let me try that again. Anything with respect to Y, anything with respect to Z, there we go, goes away. And we're just left with the X derivatives and the time derivatives. And so we get this. And so that's now the equation that we're going to solve. Okay. So starting here, how do we solve this guy and get something that we could actually use to figure out what the temperature is in an object, both with respect to location and with respect to time. That's the big goal, right? Is to try to figure out what the temperature field of this object looks like with respect to time and temperature simultaneously, right? It's actually pretty awesome. So notice, right, we have a second order here in spatial and a first order here in time. So this equation requires two spatial boundary conditions and one initial time boundary condition. And we're solving for t as a function of x spatial and small t time. And so that's the ultimate goal, is to get the temperature field versus spatial and time dimensions. Okay, so a common initial condition on the object's temperature is that we just assume the thing is just uniform temperature at the beginning of whatever process we're trying to interrogate. So in terms of the math, that means that the temperature at any x at time equals 0 is equal to some initial temperature, right? So the whole thing is this uniform temperature. To illustrate that, I've got a plane wall here, and you can actually see a temperature profile kind of evolving with time. And initially, the entire plane wall is fixed at Ti or T initial. And then as the process proceeds forward, you can see that the temperature starts to go down. But initially, the whole thing's at constant temperature. So that's visually what this equation means. A common spatial boundary condition is symmetry, right? So if I've got a plane wall and I've got the same temperature and the same convection coefficient on both sides of the plane wall, what that means is the center line of the wall is a line of symmetry. So the temperature profile is going to look the same on the left of that line as it does on the right of that line. And because the temperature profile looks the same on either side of that line, that means that the derivative at x equals 0, which is that spot of that center line in the x direction, has to be 0. So that's what this boundary condition is saying to us, that the derivative of temperature with respect to x at x equals 0 is 0, right? So that just tells us that we've got a peak in the temperature profile at the center line here. So that's what this one means. And then the second common spatial boundary condition is the one that occurs at the boundary, right? So here we've got a convective boundary, and you guys have seen me do this before, where I say, okay, I'm going to set the conduction at the surface equal to the convection at the surface. That's just the first law energy balance, and that's what this equation is, right? So I've got the conduction k dt dx at x equals L. So x equals L is this edge, is equal to t at x equals L minus T infinity, right? So that's Newton's law of cooling, H delta T. So that's the convective heat transfer off of that surface. They're equal to each other. And so that gives me that second boundary condition. Okay, and so what we get from kind of walking through the origin of this equation and then also looking through these boundary conditions is the realization that spatial and transient temperatures in solids depend on multiple physical parameters. So there's the temperature itself, which is what I'm trying to solve for, and then there's a spatial dimension x, there's a time dimension t, there's the initial temperature, right, which comes from this boundary condition. There's the ambient temperature, T infinity, which comes from here. There's L, which is the physical length of this object. There's K, the thermal conductivity, alpha, thermodiffusivity, and H, right? Those all kind of live in these various equations, right? So we end up having 1, 2, 3, 4, 5, 6, 7, 8, 9 variables that we care about. Okay, so if you guys took fluids with me, you know what's coming, right? Which is if you have a complicated system with a lot of variables, the best way to kind of deal with those variables, to simplify them, to process them, to make the problem more tractable, is to apply the Buckingham pi theorem and just non-dimensionalize everything, right? So just as a quick reminder, an equation of n variables that are dimensionally homogeneous can be reduced to relationships of n minus r independent dimensionless products where r is the minimum number of fundamental dimensions. That is the foundational statement of the Buckingham pi theorem. And here's the equation. Basically what it says is you get some number of pi terms. So these are dimensionless terms. And the way that you know how many terms you get is you start with however many variables your problem has, right? In our case, it's 9. And then you subtract out the number of fundamental dimensions, right? So this is LMT theta, right? So there's 4 LMT theta. Yeah, there's 4 is the maximum really that you could have for like an energy thermal fluids type problem. And so we expect there to be 5 terms. I'll actually show you there's a trick to get us to 4. But this reduces the experimental space with no loss of information, right? So again, if you guys had me in fluids, we like beat this to death and we used it all the time because this is probably my favorite principle in all of like fluid mechanics. So we're going to use it in heat transfer to make our Biot number sadness a little less sad. Okay, so I'm not going to go through these. If you had fluids, you've seen this already, but this is just for your reference, the step-by-step process of carrying out the Buckingham pi theorem. So here's the first 3 steps. Whoops. Okay, here's next steps 4 and 5. And then finally, step 6 through 9. And ultimately, right, the goal of this is to take the number of experimental variables, which for us is 9, and reduce it from that number to n minus r, which is an overall reduction in problem complexity. And you get the benefit now of having dimensionless variables. And again, if you took fluids with me, you know, if you've got dimensionless variables, they're super useful because you only have to solve the problem one time, and that solution is valid for every similar shape of every possible other problem that you could imagine. Provided you've got similarity, you just have to solve it once, and then you've got the solution for every other possible configuration that illustrates similarity, right? So incredibly, incredibly powerful technique. I don't know why it's not the very first thing taught in any engineering class in freshman year, but it's not. You have to wait until fluids to get it. Okay, so we're going to do Buckingham pi. I'm not going to go through it in gory detail. I'm just going to give you the results. I trust that if you've taken fluids, you know how to do it. One trick that I'll describe is initially we've got 9 variables, but we know from right before I described to you that law of conservation of chalk trick, where you could take the temperature of whatever it is you're trying to solve for and subtract out the free stream temperature, the temperature in the air surrounding the object, and get this thing called theta, right? So we're going to do that, and we're going to end up reducing the number of variables here from 9 to 8 by basically taking t minus t infinity and t initial minus t infinity and calling that theta and theta I respectively. And so that gets us to 8 variables, right? So we've already eliminated one variable by just doing, law of conservation of chalk. So we've got theta, which is what we're solving for. And then we've got 1, 2, 3, 4, 5, 6, 7 more variables. So a total of 8. We're going to select MLT theta, although it doesn't matter, right? This will work with FLT theta as well. But, for us, M is mass, L is length, T is time, and theta is temperature. And all of those are present here, right? So we've got mass, thermal diffusivity has mass in it. Here's lengths, right? Length scales. Here's time. And then theta obviously has temperature in it. So we've got all 4 fundamental dimensions. So for us, R equals 4. And so if we actually carry out the Buckingham pi foundational theory, we get 8 minus 4, which is 4. And so what we're expecting out of this is 4 dimensionless numbers, 4 pi terms. So that's exactly what we get. So again, I'm not going to do it. I'm just going to give you the result. You guys can walk through it as an exercise if you want to. It is awesome. But you end up with theta star, which is just the ratio of the temperature differences. And then you get X star, which is X divided by LC, right? So X is like the variable, like the spatial dimension of where you're located in the object, and then LC is like the overall characteristic length of the object, right? So that's dimensionless length. Then we get dimensionless time, right? Alpha T over LC squared. This you should recognize as the Fourier number, right? I had it somewhere. Maybe there it is, right? So there's the Fourier number that we've already seen. Should not be an enormous surprise that it pops out of the Buckingham pi theorem because it's a dimensionless number that's representative of time. So there it is. And then we have the Biot number, right? Also not an enormous surprise that that pops out because this is a dimensionless number that we've already used to characterize these time dependent thermal conduction problems, right? So like literally these are like old friends, right? It's just four variables that we already recognize from previous types of analysis. So that's what pops out. So in the end, we now have taken our 9 variable problem, and through application of Buckingham pi, we've shrunk it down to a 4 variable problem where we're still doing the same thing we were doing before. It's all now just simpler and dimensionless. So we're looking for a dimensionless temperature, which is a function of a dimensionless location, a dimensionless time, and then a parameter that's equating the basically the magnitude of the internal temperature gradient to the heat transfer and the heat flux external to the object, right? So, or if you will, like conduction versus convection ratio. Um, of course, Buckingham pi does not tell us what this functional relationship is, but it does tell us the important variables. And normally, like back in fluids, you'd actually have to run an experiment to figure out what this functional relationship is. In heat transfer, we know what the functional relationship is because we have the diffusion equation, right, which relates all of these variables to each other through an actual mathematical equivalency that arises. If you go all the way back, it's from application of the first law of thermodynamics to an elemental particle that we're then interested in conduction through. And so I do have to now take this and non-dimensionalize it. So that's this step, right, where I'm just taking my T and non-dimensionalizing it as theta star. I'm taking my X, non-dimensionalizing that as X star. Oh yeah, I was like, why is it squared? Because this one's squared, right? They're both squared. And then 1/alpha is still in there. And then I'm taking my time and I'm making that dimensionless by making it a Fourier number, right? So this expression and this expression are equivalent, no loss of information. The only thing that I've done is replace the dimensional variables with the dimensionless variables so that I have to deal with fewer overall variables and make the problem much simpler on myself. Okay, so I've now converted the foundational equation, right? This is F. I now have to solve this. And so I have to also convert my boundary conditions, right? So that initial boundary condition that was the convection boundary condition, right? So the conduction out of this surface has to equal, or let me try again, the conduction into this outer surface has to equal the convection out of this surface. That's this boundary condition. So I'm just going to go through and non-dimensionalize that, right, the way that I did up here, just replacing the dimensional terms with the dimensionless terms. And then here is my my symmetry boundary condition, right? The one in the middle here, that the derivative has to equal 0. So just non-dimensionalizing temperature, non-dimensionalizing X with theta star and X star, same deal. And then here is my initial temperature condition for the whole object, which is that the whole object was at some uniform temperature all the way across. So I'm just replacing my at time equals 0. So I'm just replacing my dimensional temperature with theta star and my dimensional location X with X star. And this it just goes to 1, right? It can't be any simpler than that because I've non-dimensionalized it, right? So if I look at what theta is, let's go back and remember what theta is, right? So all I'm doing is just saying, okay, the initial temperature minus T infinity over the initial temperature minus T infinity. That's just 1, right? So that's why this is 1. Okay, cool. So I've got this all set up now, right? It's all non-dimensionalized. It's all boundary conditions are all redefined in terms of my dimensionless variables. My life is good, sort of. So I can come up with an exact solution. So I say here, exact analytical solutions to transient conduction problems are attained for many simple geometries and boundary conditions, right? So these solutions are known for slabs, like uh, cylinders, spheres. Like you could go into the literature and you can actually find these solutions for a lot of common shapes. The book just uses those three. So plane walls, which I call a block or a slab, um, cylinder and sphere. So that's problems that we'll encounter in this class are basically going to be based on that geometry, but you could definitely find other solutions for other slightly more complicated geometries. You get to the solutions by, again, like solving this differential equation, which can be done using something like separation of variables. Happily, we are engineers and not mathematicians, and so we don't have to do that, right? We rely upon the mathematicians to solve the problems for us, and we take the solutions and then we use them and apply them in real world situations and solve heat transfer problems. So it turns out a little bit, unfortunately, that the exact solutions to these transient problems are, yes, infinite series, just like we encountered in the two-dimensional uh, temperature field of a flat plate a couple chapters back. These solutions are also all infinite series. Um, so that is challenging because if you actually solve the problem like correctly in the most extreme case, you basically have to sum up an infinite number of terms, which will take you forever. But again, haha, we're engineers, not mathematicians. So what are the three words that describe engineering? Good enough. And it's only two words, and that's part of the joke. So good enough or close enough. So for sufficiently large Fourier numbers, and by sufficiently large, I mean Fourier numbers that are greater than about 0.2, this is not a hard and fast limit. This is more like a rule of thumb. But if you're up above 0.2, what that means is that the um, process is long enough in time, right? Because Fourier number is dimensionless time, and time is in the numerator of Fourier number. So we're talking about a long time. It's long enough that it turns out that all of the higher order terms in this infinite series decay really rapidly. And the only thing that you need to worry about is the first term. The first term is the only one that really matters because it's so much bigger than all the other terms, typically for this condition of Fourier number being greater than 0.2. And so most of the time, that's the situation that we'll find ourselves in if the Biot number is greater than 0.1. The next thing we'll do, of course, is check the Fourier number to make sure that this condition is true. Normally it is, because not all, but most engineering heat transfer processes occur over, seconds. And so we'll end up with a large enough Fourier number that this is correct. So we're going to do these first term approximations, and that's going to be like the bread and butter of how these problems are solved. But just so that you can see how it's done and see where that first term approximation comes from, I think it's important to walk through the entire exact solution just so you can see how it's done. Okay, so we're going to do three of these. The first one is going to be a plane wall, then we're going to do a cylinder, then we're going to do a sphere. They're all basically the same. Once I do a plane wall, we'll be able to kind of, really fast go through cylinders and spheres because the process is the same. Geometry is just different. Some of the equations are a little different, and I'll point out those differences as we go. Okay, so imagine we have a plane wall like this one, right? So it's a I call them a block that is 2L thick, right? So x equals 0 here is at the center line, and then negative L to positive L is the thickness, so 2L thick, where the thickness is small relative to the width and height, right? So this thing is much bigger up and down than it is in the x direction, and it's also much bigger into the page than it is in the x direction, right? So you need it to be, infinite, semi-infinite, for this to actually, be perfectly true, but it'll work even for objects that aren't necessarily, infinitely big or infinitely wide. Um, and I'll show you later. There's a criteria for that, which we'll see with cylinders. So anyway, we've got this block that is uh, wide and tall, and then only 2L thick. Conduction occurs exclusively in the x direction, right? So it's only going to have a temperature gradient or support a temperature gradient in this direction, the x direction. And so if the initial temperature, so T for the entire system, so for any x at time equals 0 is T initial, and the block is suddenly immersed in a fluid that has temperature T infinity. And of course, that T infinity has to be different than T initial, or else nothing will happen. The resulting expression for temperature as a function of x and t is of the following form, right? So here it is, right? And I'm not going to go through how this was solved. Just, a mathematician did this for us, and we're going to benefit from that person's solution. If you really wanted to, you could do this yourself using separation of variables, but we are engineers, not mathematicians. We don't have to. The solution exists, and we're going to use it. So this is, again, an infinite series. It has this thing in it called zeta. We'll talk in a little bit about, what in the heck is zeta. Zeta turns out to be a function of the Biot number, which presumably you already checked if you got this far, right, to discover that the Biot number is less than 0.1. So it has x star in it, which is the spatial coordinate. It has Fourier number in it, and then it has this thing called Cn. Well, Cn is just a constant, and that constant is given here. And of course, it's different for plane wall, cylinder, sphere, but it's just a constant. And it's a constant of this thing called zeta, which again, we'll talk about that and where it comes from here in a second. But notice that there's this little n here, right? And there's this little n here, and there's this little n here. And what that means is that each time you index n, you have to find a new value for Cn, a new value for zeta, and then you have to sum them all up for a particular dimensionless location and dimensionless time, right? So you're basically solving for the temperature at a spot represented by x star and a time represented by the Fourier number, and that exact temperature is just based on an infinite sum of all these terms. So if you do this, this is true for all Fourier number, right? This is not limited by Fourier number greater than 0.2. This is from 0 out to infinity. This is the exact solution, right? And it's right for basically all time. So if you do have a process that happens in a very short time, this is the way to tackle it, right? If the Fourier number is less than 0.2, you got to go to the exact solution and solve the exact solution. It's onerous, but it's not impossible. It's not the end of the world. Okay. So this is, just sort of a summary of those equations that I showed you before for a plane wall. I promised I would tell you what zeta is. Here's zeta, right? So zeta turns out to be a function of the Biot number. What function of the Biot number? Well, it's different for plane walls, cylinders, and spheres. This is the equation for the Biot number, sorry, for zeta. For a plane wall. Yes, it's transcendental, which means you can't actually just solve it directly. You have to solve it iteratively. The good news is it's already been solved for us, right? So in your book, you'll find the first four roots of the transcendental equation, zeta, tan, zeta equals Biot number for plane wall conduction, transient conduction, right? So I want to emphasize and reiterate that zeta is a function of Biot number, and you already know the Biot number because we're here because your Biot number was wrong, right? Your Biot number was not small enough that it allowed you to do lumped capacitance. So you already calculated Biot number to get here to begin with. Here's the table, right? So here's all the Biot numbers, and then here are the first four zetas for those Biot numbers for this transcendental equation, right? So already been done for you. I will show you when we get to cylinders and spheres. If you wanted to calculate this for yourself, you could. There's a way to do it. I do it in Excel. That's how like old school I am. Um, I'll show you how to do it. Um, Notice that we only go up to four, right? There actually, right, are infinitely many of these zetas, but as I mentioned, these higher order terms fall off very fast. And so whoever made this table was like, nah, you don't need any zetas bigger than four because those terms are going to be so tiny that they're not even going to contribute to a meaningful engineering solution, right? So even the guy who wrote the textbook was like, you don't need more than four terms for this. You can find them if you want to, but trust me, they're going to be tiny and you don't want to add them because they're not going to help. Okay. So that's a lot, right? And you might be saying to yourself, like, oh my God, I should have like transferred into electrical engineering. What am I doing here? And so this is that point when the heat transfer is just a little too much. So um, you might someday have to do the exact solution, but for the most part, these problems are solvable using the first term. So these are called approximate solutions. So we're going to find the approximate solution for the temperature field of a plane wall. And now remember, this is true only for Fourier numbers greater than about 0.2. But that's almost all situations, right? So very rarely do you have to do this. So you can get away with using the one-term approximation, and your answer is close enough. Typically for engineering applications, if Fourier number is greater than 0.2. So what happens when the Fourier number is greater than 0.2? What that means is we're going to take this monster and we're going to just approximate it as the first term. So C1, zeta 1, and we're going to throw out all the higher order terms because they're tiny compared to the term that's associated with C1 and zeta 1. Right. So you can compare, right? So all I'm doing to get the exact solution, to get the approximate solutions, I'm taking what's inside the summation, right? So Cn e to the minus zeta squared Fourier times cosine of zeta x star, right? Boom, there it is, right? And I'm just getting rid of the summation, right? Because I'm not summing anything anymore. I'm just using the first term, right? So there it is. And it'll turn out, we'll see this later on, all of these all are very similar in that they all have this initial C1 times e raised to the minus zeta squared Fourier. They all have this term in them. What makes them different from each other, what makes a plane different from a cylinder, different from a sphere, is they have this add-on term called the shape function, right? So, whoops. So the shape function is in the exact solution and it just pops out and comes along with us. So this is the one that changes depending on what your geometry is. Okay. So how do we solve these things in a way that is actually tractable and doesn't turn us into Frodo making his way to Mount Doom? So we're going to start out with the block's midline, which again is this spot here, right, for the center of the plane. And that is the spot where x equals 0. And so x over L is x star. And so that's the spot where x star equals 0. Aha, look at this, right? So I've got cosine times this nasty zeta thing times 0. Cosine of 0 is 1. Aha, right? So this whole term just goes away at the center line, at the midline. And what I'm left with is that theta star at x star equals 0 is just this initial term, right? Just that all by itself, right? There it is. Okay. And the implication here, which is incredibly useful and powerful, and we're going to use this a lot when we solve these approximate solutions, is within the one-term approximation, all spatial locations exhibit the same exponential time dependence, right? They all have this term in them, right? Notice there's no x anywhere in here, right? No x. Only the spatial multiplier differs, right? So only the shape function of the spatial multiplier differs. And so what we're going to do is basically every time we encounter one of these things, if we're interested in the temperature at some spot other than the middle line, we're going to first solve for the temperature at the midline at the time that we're interested in. And then we're going to just multiply that by the shape function, the spatial multiplier. And that's going to get us the temperature at whatever location we happen to be interested in, right? So that's kind of the sequence of how we're going to go, right? We're going to first check the Fourier number, make sure that we can use the one-term approximation. We're going to get to the one-term approximation. We're going to take the Biot number, and we're going to determine the zeta and the C for, plane wall, infinite cylinder, sphere, whatever our geometry happens to be. Plug all those values into this equation to get the temperature for some Fourier number for some time at the center. And then we're going to multiply by whatever the shape function is, right? It happens to be cosine for the plane wall to get the temperature at whatever time we're interested in, whatever Fourier number we're interested in at some other location inside the wall, right? So that's the sequence. And just as a quick reminder, right, this is the Biot number chart. Zeta is a function of Biot number, which I'll show you in a second. C is a function of zeta, which is a function of Biot number. So all you have to do is just plug in your H, L, and K, find the Biot number, and then go to these charts and look up the appropriate zeta and C, plug it in here, and that gives you the centerline temperature for a particular Fourier number, right? This looks really daunting, but it's actually like, it's not too bad, right? It's once you like walk through the process, it's got kind of a cadence to it that makes it, pretty tractable. And I should mention, right, this was all set up to be easy for engineers to do because this was all created in a time before there were computers, right? Before anybody had any copy, even before calculators. This calc was all developed in the 1950s. So before anybody had the ability to do any computation. So this was intended to be done by hand. Therefore, it is pretty simple. Relative to some of the other things that you have to face as an engineer in 2026. Okay. Cool. So, we've now got a way of getting the temperature field. So the temperature at any location in a plane wall at any time in the plane wall, provided the entire plane wall started at uniform temperature and is subject to these boundary conditions, right? So some fluid at T infinity with some convection coefficient. Remember, our big goal in heat transfer is to get the temperature field, so temperature, and then also to get the heat flux, right? So we've got the temperature figured out. Now we have to get the heat flux. So the approximate solution for the heat that is either absorbed or rejected by a plane wall is come up with in the following way, right? So we're going to just take the total energy that has left or entered a block up to any time t, and we're going to figure that out based on this control volume that we're going to draw around our block, right? It actually doesn't really end there. It's infinite up and infinite down and infinite into the page. But for our purposes, just for the derivation, we're going to draw. I can't draw infinitely big boxes, right? So we've got a finite size box. So we're going to apply the first law of thermodynamics to this, and out will pop this heat that gets either absorbed or rejected depending on whether you're heating or cooling the brick here. Okay, so the change in energy of this system is the energy at whatever time we're interested in minus the energy that the block had at the initial time, and that's going to equal Q in minus Q out plus W in minus W out. You guys, I think, have heard me enough times say when you write the first law of thermodynamics, do not just write delta E equals Q minus W. That's not right. Your thermo professor lied to you. It's not just delta E equals Q minus W. It's Q in minus Q out. It should actually be plus. We'll change that. What slide is this? 18. Plus W in minus W out. That Q minus W thing, that's for cycles. This is not a cycle, right? So I really, really encourage you to write the whole thing out and then cross out the terms you don't need. You'll never make a mistake if you do it my way. There's no heat entering, right? This is a block that was hot to begin with and is cooling down. So no heat is entering, but heat is definitely leaving. So this term stays, and then there's no work transfer, right? So those two terms go away. So what we're left with is that Q out is equal to minus E at whatever time we're interested in, minus whatever energy that the block had at initial time. This negative sign is this negative sign sitting in front of Q out. And I know that the energy for a closed system, which this is, right? It's just a solid. It's just the internal energy, and the internal energy is just mct, and m mass is just the density times the volume. So here's my expression for energy. I'm going to take this, I'm going to plug it back into my first law of thermodynamics, and this is where things get a little bit weird. I instead of like taking the whole volume of this thing, I'm going to just look at a little differential piece of volume, so a little dV, and then I'm going to integrate over the entire volume, right? So I've got Q is equal to this energy difference, right, which is here. Um, Here it is represented as the energy of a little differential volume, and then I'm just going to do the integration. Okay, so that's how I get to Q. Now, because I non-dimensionalized everything else, right? It's like Days of Thunder, right? Hit the pace car, hit the pace car, hit the pace car. You've hit everything else out there. I want you to be perfect. Right now, I'm really dating myself. Um, we want to non-dimensionalize Q because why not? We've non-dimensionalized everything else. So it's convenient to assume constant properties, right? Which allows us to actually do this integration without a lot of drama. And we want to non-dimensionalize by the maximum energy that could be transferred to the plane wall if the process continued out to infinity, right? And we know what that is because that's the time, or that's the amount of heat that gets absorbed once this thing is sat in this fluid for an infinite amount of time and it's reached T infinity, right? So that's what that is. And so now we're going to just carry out the same integration, except we're going to do it as a non-dimensional heat. So it's the Q that we're actually interested in, non-dimensionalized by the total possible heat that could be absorbed for an infinite amount of time. And we'll carry through the integration. So we go from this step to this step. Notice that I've got T minus T initial and T initial minus T infinity. And I can do some manipulations, and that works out to be 1 minus theta star, which is very exciting because I already have theta star in my analysis, right? So, and then when I finish the integration, I'm left with, so I can just take, right, my expression for theta star, right here it is, right, theta star, and I can plug it in and do the integration, and this is what pops out, right? So I've got 1 minus sine zeta 1 over zeta multiplied by C1 times e to the minus zeta 1 squared times the Fourier number. And right, this thing here is also theta star, right? It's also theta star, right? Yeah. So I can write this either way. I can write it either as this exponential, or I can write it as the temperature ratio if I want. But that's it. That's my dimensionless heat. And then if I want to get the heat out, I just figure out what the total infinite time heat absorption would have been and just multiply that by this guy, and that gets me the heat that I've absorbed, right? So, okay, voila, that's it. So I've now got a way to get the temperature field, and I've got a way to get the heat absorbed or rejected, depending on whether you're heating or cooling. So I've satisfied the requirements of typical heat transfer problem for uh, spatial and temporal dimensions. Wow. Okay. So what I showed you before is all equations. You could also do this graphically. So those equations have been basically converted into a series of charts. So here they are. And so approximate solution, block midline temperature. So these graphs illustrate the functional dependence of the midline transient temperature T at x equals 0 of whatever time you're interested in, relative to the BO number and the Fourier number, right? So these charts are just a graphical representation of this relationship, right? Which is what we got from the Buckingham pi theorem, which is what we've been trying to solve all along. And they happen to be the solutions for the midline temperature, right? And remember, why do we care about the midline temperature? It's because you can take the value for the midline temperature, multiply it by the shape function, and get the temperature anywhere else. So how do these work? Okay, so we're going to look across the bottom here. These are Fourier numbers Fourier numbers. We're going to look at these numbers that are kind of embedded in the lines here. Those are inverse Biot numbers. And we're going to look over here. These are theta star at x equals 0, right? They move along this way. And then this little inset here, right, is just a blown up version of kind of what's over here, right? So this is broken out here just so that you can see the detail, right? Because all these lines kind of collapse on each other, right? It's hard to tell the difference. So that's what this is, just a little inset to show you the detail of this upper corner. Okay, so right? So how do we do this? Well, we figure out because remember we're just worried about the midline, right? The mid center line of our block for this chart. So for some dimensionless time, that's a Fourier number, we're going to read across the bottom. And then for some Biot number, we're going to pick the appropriate line, right? So, right, 4, 5, 6, 7, 8, 9, 10, these are all Biot numbers. And where the Fourier number and the Biot line cross each other, we're going to read over to theta. This is theta star at the midline. And that's going to give us the dimensionless temperature, or if we want the dimensional temperature at the midline, right? So you can imagine doing this or doing the calculation, using the equation. Either one is correct, but these are both just different ways of representing the same information. Okay, so now how do we get the graphically the value for a temperature that's off the midline? Well, so I say if t at x equals 0, comma time is known for Biot number and Fourier number, right? So we figured that out from here. Corresponding temperature at any location, t of x and time, can be found. Corresponding internal energy Q can also be found. So one way to do it, as I said before, is to just multiply by the shape function. The other way to do it is that these are shape functions, right? And lo and behold, this is like a cosine, right? And look, it's a cosine, right? It's the same exact shape as a cosine. It just gets expanded or contracted based on this ratio of x over L, right? So what do? We've got our theta star at x equals 0, and then we just take our theta star at x equals 0 and get the inverse Biot number, get x over L. Where those cross each other, that gets us the appropriate theta value, right? And these curves here are the midline temperatures, right? So the theta star values from the previous chart, right? And of course, it doesn't go above 1 and it doesn't go below 0 because theta star is just the dimensionless temperature bounded by 1 and 0, right? So that makes sense. Okay, so that's how to get the temperature at any spot. To get the Q, same idea, right? So we've got in the x-axis here this kind of weird dimensionless number, which is a Biot number squared times a Fourier number. So here they are. Notice it's logarithmic, right? So be careful. You've got logarithmic on the x-axis. And on the y-axis, we've got our Q over Q. That's what we're actually trying to solve for. And then these are all just Biot numbers, right? So for any, and let's just look back and make sure that we've convinced ourselves, right? So this guy is a function of zeta, which is a function of Biot number, and a function of t, which is time, which is Fourier number. And so any Biot number squared Fourier number gets us here, and then the Biot number gets us here, and where this guy crosses this guy, we read over, and that gives us our Q, right? And again, bounded by 0 and 1. Why? Because we've non-dimensionalized this. The maximum amount of heat that could possibly be absorbed is if we let this thing go to basically infinite time, right? So infinite time is way up here at the top, right? Where Fourier number gets just really big, right? You can see these sort of go off asymptotically to infinity, but right before infinity, they're those values for 1. And then if you give very little time, right? Fourier number is very little or 0, then all these guys collapse to 0, and you've absorb no heat, right? Because you haven't given enough time for the heat to um, convect or conduct into your object, right? Okay, so internally it's all self-consistent. Again, these are just graphical representations of these equations and these equations. So you can do it either way. There are no exams in this class, but I imagine if you were in an exam, you'd probably want to use the graphical approach, right, rather than the equation approach, just because I think it's probably faster and less prone to error. But that's up to you. But happily, we don't have any exams, so you'll never have to worry about that, at least not in my version of heat transfer. Okay, so I give just a little example here, so which is just generic. So to find the surface temperature, which is the spot where x star equals 1, right? Because x equals L, so L over L is 1. At some time t, you first determine the midline temperature at that time, right? So you go back here, determine the midline temperature at that time. And then you use the figure on the left to determine the surface temperature, right? So that would be the line x over L, so L over L is 1. So you're on this line, right? And you know the BO number. So from the BO number and where you are on that line, you read over, and that's your theta value, right? Okay, so that's how that's done. All right. Cool. So we're done with slabs, plain walls, and now we're going to move on to cylinders. Okay, so in the table that we've looked at before, we've seen this term infinite cylinder. Infinite cylinder. What do I mean by infinite cylinder? Well, it's a cylinder that is much longer than it is wide, right? So its length is much greater than its radius. And so this ratio of length to radius has to be greater than or equal to 10. And that gets us, more or less the infinite that we need for this all to work, right? Same idea with the plane wall, right? It has to be much thicker and longer than it is wide. So the cylinder has to be much longer than it is in radius. So for an infinite cylinder of radius R naught at initial uniform temperature and experiencing a change in convective conditions, the exact solution can be obtained. Typically, the solution is infinite, except for a number less than 0.2, in which case, for a number less approximate solution can be done by a single term, right? So this is the exact same statement from the previous example for a slab. The only thing that changes is we have R instead of X, or I should say R star instead of X star, because R star is just R over R naught. R naught, by the way, for the cylinder is the outside radius of the cylinder. Okay, so for conduction occurring exclusively in the R direction, because we have an infinite cylinder, the resulting temperature field, so this is now temperature as a function of R and T. So what we're looking for is the temperature at any spot at any time, provided the Fourier number is longer than 0.2, is the following form, right? And again, the math was done by mathematicians. You could use separation of variables to solve the heat equation, the diffusion equation in cylindrical coordinates, and this monster would pop out. And I'm not going to show you how to do that. It's separation of variables. Mathematicians did it. Thank God. We don't have to. We can just use the solution for our purposes, which again is to find the temperature field for our cylinder. Okay, which is here, right? So theta star is dimensionless temperature, and notice it's very similar to the equation for a plane wall, except instead of cosine sitting out here, we have a Bessel function, and you've seen Bessel functions before, right? They popped up before when we were doing exact solutions for temperatures in 2 dimensions. 2 spatial dimensions. So you know how to handle them. typically the Bessel functions are just tabulated, right? So in your book, here's a table that has Bessel functions of the first kind. So Bessel function 0, Bessel function 1, and then the x is the thing that the Bessel function is actually acting on. So that's what lives inside the parentheses here. So in this case, this Bessel function, you take zeta n times r star, and then that's your x value, and then you look up the value for Bessel function based on that x value, right? So that's where those come from. I've got this box to remind me to show you something in the next slide. So don't worry about this red box just yet. We'll come back to this in the next slide. Okay, so just like before, it's an infinite series. C is some constant. Um, yuck, right? But not impossible, right? C is just a function of zeta, and zeta is just a function of Biot number. We are now taking the zeta and plugging it into Bessel functions, zeroth order and first order Bessel functions. Sometimes we're squaring the Bessel functions, right? So but right, not impossible. Just a mathematical equation. You guys can look up these values and plug in and solve for C1. Zeta, in this case, is still just a function of the Biot number, and it is the solution to this guy, right? So Bessel function sub 1 of zeta divided by Bessel function sub 0 of zeta multiplied by zeta, that's should equal the Biot number. So again, this is a transcendental function. You can't solve it directly, but you can solve it iteratively. And again, I'll show you once we get into cylinders. Once we get into spheres, I'll show you how to solve this if you really need to. But normally you would just look these values up, right? So they, oops. So right, they live right here, right? So here's my various possible values of Biot number. And then here's for an infinite cylinder, here's zeta 1, and then here's C1, right? So they're all tabulated for you. You don't usually have to do this math, but just so that you know where they came from. This happens so rarely that our book doesn't even tabulate zeta values for this function, right? So they give you just this guy. So zeta sub 1 for Biot numbers. They don't give you any of the high order zetas, no zeta 2, zeta 3, zeta 4, like we got for plane wall, right? This doesn't exist in our book for a cylinder or a sphere. But they give a reference, right? Which is conduction heat transfer by P.J. Schneider, published in 1957. As described, this is all work done in the 1950s, all meant to be done by hand. Or you could just use AI, right? To just say, hey, bro, like, what is this? And AI will presumably give you the values. But I'll show you how to calculate them in a second. Okay. So this is, again, right, a lot. And you don't actually need to worry about this unless your Fourier number is smaller than 0.2. If your Fourier number is bigger than 0.2, right, which is most engineering processes, you could do a one-term approximation just like you did with a plane wall, right? So like I said, we're going to see the same pattern a lot. And so I won't go through this one in as much detail as I did the last one, but just to give you a sense, right? Here's that same expression for theta. Where does it come from? It comes from the infinite series, except we're no longer taking a sum from n equals 1 to 1,000 or 1 to, sorry, n equals 1 to infinity. We are just taking that first term. So C1, zeta 1, just the first term. And for Fourier number bigger than 0.2, the first term is much, much bigger than all the other higher order terms. And so it dominates them, and we don't need to worry about those other terms. It's typically the approach. We're going to do the same thing we did before in terms of determining the center line temperature. Once you define the center line temperature, then you can use the shape coefficient here, just like we did, shape function, just like we did here before for the plane wall, right, to get the temperature or the dimensionless temperature for any location, right? Any location inside the cylinder. Okay, so for the center line, um, R star equals 0 because R equals 0 because we're at the center, right? So R equals 0 at the center. And so it turns out that the Bessel function of 0, right? Because zeta times 0 is 0. Bessel function of 0 is 1, right? And that's why I boxed this to point out to you that if you plug in 0 into Bessel function of the 0th order, you get 1, right? So that's where this 1 comes from. And this whole term, just like cosine 0, right, becomes 1. And then the centerline temperature is just this term all by itself. Now, I'm going to point this out again later, but just so that you see it, C1 e to the minus zeta 1 squared Fourier for a cylinder, oh, it's the exact same for a plane wall, right? And it'll actually end up being the exact same for a sphere too. So you can see, right, this initially looks like incredibly complicated and overwhelming, but it all collapses into just like a single solution path, regardless of whether you're a plane wall, a cylinder, or a sphere, or cover other common shapes, right? So this combination of variables is exactly the same. So how we do this, we determine our BO number for a cylinder, right? It's H R naught over K. We come here to our BO number table. We look up the appropriate zeta, no, over here, the appropriate zeta and the appropriate C1 for infinite cylinder. We take zeta and C1, we plug it in here, we solve for temperature. This is our dimensionless centerline temperature. And once you have the dimensionless centerline temperature, whoops, wait a minute. Huh. Okay, once you have the dimensionless centerline temperature, sorry, blah, blah. Once you have the dimensionless centerline temperature, you can go back and multiply by the shape factor that gets you the temperature at any location that you're interested in. Okay, ooh. And you can do the same thing that you did for the plane wall for the cylinder in terms of heat, right? Because this is now the temperature field solution. So we're interested in how much heat we can absorb. So same story, right? Apply the first law of thermodynamics now to our cylinder. And then we're going to do the same thing we did before, non-dimensionalize the heat by the total heat that could be absorbed if we let this cylinder soak for an infinite amount of time. Here's that ratio. We do the integration. The only thing that changes in the integration is that this theta star is now the theta star, here it is now the theta star for a cylinder instead of a plane wall. And when we do the integration, out pops this guy. And this is the expression. Notice it's got, Bessel functions and zetas in it. That's fine because we can look up what those values are. Multiplied by this kind of common centerline temperature term, or because we know that this common centerline temperature term is just the theta star, right? These two are equivalent to each other, right? This and this are equivalent to each other. So we can do this either in terms of the temperature of the spot at that time or in terms of this guy, right? So that's the heat for a cylinder. Okay, just like with the plane wall, I can also do this graphically, right? So I have the same equations that I had before, and here is my note. So my note is, since the one term theta star equations for the block, which is the plane wall, the cylinder, and the sphere are all the same, their graphs are identical, right? This actually screwed me up in the beginning. I'm like, did I just copy and paste the same thing 3 times? And yes, I did, because it's the exact same chart. Why? Because this equation for the midplane or the center line or the center of a sphere, mid plane of a plane wall, or the center of a cylinder is the same, right? I pointed this out before. It's same here, same here. And if we go forward into the world of spheres, too far. Same here, right? It's the exact same term. So again, everything sort of collapses into like just a single solution pathway. So you only need to see this chart once, and you can already apply it to planes, cylinders, and spheres. Okay, and the solution process is exactly the same, right? You figure out the time that you're interested in. You figure out the BO number, which you've already calculated to get this far. You look to see where the Fourier number based on the time and the BO number cross each other. You read over and you find theta, which is the midline temperature. And then you take that midline temperature and multiply it by x over L. So this is now your spatial location anywhere inside the cylinder. I'm going to check if it's actually x over L or if it's r over L. Just check that. I may very well have copied the same thing 3 times over. Let me check on that. This should be r over L, but it might just be the book that left it at x over L. So I say if T naught r equals 0, T is known for BO number, Fourier number, which it is from the previous slide. Corresponding temperature at any location in the cylinder can be found. Corresponding internal energy change, Q, can also be found, right? Same idea as before, right? Okay. Okay. Last one. So this is a sphere. This verbiage is exactly the same as before, so I won't even bother reading it. This equation, again, is an infinite series for the temperature field of a sphere. You only have to do this if the Fourier number is less than 0.2. This, again, is solved by a mathematician, separation of variables. We don't care how it was done. We just care what the answer is. Here's the answer. We can now use this to our advantage to solve for the temperature field. C1 is just a constant, and it's a constant that's a function of zeta. Zeta is a function of BO number. And here's the equation for spherical coordinates, for spherical geometry for sphere, that relates the BO number to zeta. And again, the book doesn't even bother tabulating this for us, right? They just give us this table, which is zeta for a sphere and C1 for a sphere as a function of the BO number. They don't even bother with zeta 2, zeta 3, zeta 4, and so forth, because we use those so rarely that they almost never show up. But if you're interested, they are tabulated again in the same reference that I described before, conduction heat transfer. Now, what I said I would do is show you guys, if you wanted to calculate zetas, how to do it. And so let me exit out of... there we go. Okay. So I set up a spreadsheet specifically for this purpose. Okay. And I've dropped the spreadsheet into Microsoft Teams with the lecture. So if you want to like play with it, you can. Okay. So I have my BO number, and I've got plane, cylinder, sphere geometries, and I've got zeta 1, and I've got function of zeta, right? So notice, let me pull this out of the way for a second. Let me go to... Nope. Yep, there it is. Okay. So for planes, it's zeta tan zeta equals the BO number. So let me pull this over here to show you. This is zeta, C5 is zeta. So zeta tan zeta, right, equals something, right, which will become the BO number. For cylinder, notice it's zeta Bessel function of the first type as a function of zeta divided by Bessel function of the 0th type as a function of zeta. So we're looking for zeta Bessel 1 divided by Bessel 0. If we go to my cylinder, right, zeta Bessel 1 zeta divided by Bessel 0 zeta, right? So that function that I showed you is this function. And then finally, where's my sphere? Okay, so 1 minus zeta cotangent of zeta, and right, 1 minus zeta times cotangent of zeta, right? So I've got this all set up so that it'll calculate those three for you. You have to do them all. Ooh, uh-oh. No, undo. There we go. Okay, you got to do them all individually, but they're there. Okay, so how do we do this? So this is just just to sort of remind us of what the Biot number is, right? So just a value. This you would have already looked up. So let's say that we're interested in finding zeta one um, of Biot number 0.5. So the way that I do this is this is actually needs to equal the Biot number, right? So this needs to equal this. So we're going to use goal seek. Goal seek. There it is. And we're going to say, okay, we're going to set the value of this guy to BO number, whatever the BO number is, right? 0.5 by changing the zeta value, right? So again, we're going to cause this cell to iterate towards this value by changing this value. And if I click on this, it'll cruise along, boop, and there it is, right? So this guy now equals this guy, and this is the zeta that makes that happen. Okay, so I'm going to do it for this one. Let's see here. Goal seek. Goal seek. Okay, so we're going to set the value here to my BO number 0.5 by changing that zeta and go, right? There we go. Okay. And then let's do it here. So we're going to goal seek. Okay, so we're going to change the value of this guy to my BO number 0.5 by changing my zeta 1. Okay, and there we go. Okay, so the argument is that at BO number 0.5, my zeta 1s for plane, cylinder, and sphere that I got from the spreadsheet should match what's on my slide. So let's see if we can find without, okay. Okay, right? So here's that chart that's given in the book, right? And then here is right here, BO number of 0.5, and then here's zeta, right? So for the plane wall, 0.633, 0.633, right? It rounded that guy. For infinite cylinder, 0.9408, 0.94077, right? 0.940, that's rounded, okay? And then for a sphere, 1.16, 1.1656, 1.16556, right? Rounded again, right? So it's actually more accurate to do it in Excel than it is to trust the textbook because these values are obviously rounded at that last digit. But by the time you get to that last digit, the precision is, plenty good for what we're doing. Okay, so those are all of the first order zetas, right? For all of these. Now you might be wondering to yourself, right? Like, okay, we can get zeta 1, but what if, for example, I need to get zeta 2 or zeta 3 or zeta 4 because I'm actually doing the exact solution? Well, fine, we could do that too. Right, you could just look these up, but remember, they're not actually given for the sphere or the cylinder, right? It's tabulated somewhere else, but not actually given. If you had to solve for that, you could do it using goal seek, right? There it is for the sphere, or sorry, for the cylinder. So I'll just show you this one time for the plane wall because I have the tabulated plane wall values here. So yes, this says zeta 1, but you don't necessarily need to have this solve for zeta 1. You can have it solve for zeta 2 just by setting your initial guess at some value that's closer to zeta 2 than it is to zeta 1, right? So here's our BO number of 0.5. Here's our zeta 1. So if I set the initial guess to, let's say, 3, that's closer to zeta 2. And if I go through the same technique that I did before, so we're going to, we're going to goal seek, and we're going to set this cell to 0.5, that's my BO number, by changing this cell. And the only thing that I've done differently, right, is I've set the initial guess closer to zeta 2 than zeta 1. And we'll pull the trigger here. Okay, right? And I've got a BO number of 0.5, right, which is that one. And now instead of this being whatever it was before, 0.6533, it's now 3.2923, 3.9, right? Okay, yeah, so it's the same number. Okay, so the point of this is you can even use, and you guys can obviously write MATLAB or Python or whatever code you want to do this, but it's doable even in Excel using GoalSeek to find zeta values that you need if you ever have to um, find the exact solutions for plane walls, spheres, or cylinders, right? You've now got all the tools you need to do that just in case you need to. Okay, so let's get the presentation spooled back up. Let me see. I think this is where we were. Yeah. Okay. Okay. So let's start from here. Hopefully this will do that. Yeah. Okay. Cool. All right. So we walked through how to find zetas, as I said I would, and so you could actually solve this if you needed to. Um, exact solution for a sphere. However, most of the time, again, for Fourier number greater than 0.2, you can approximate using just the first term, right? And so here is, again, same as before, right? So here's the infinite series. All I'm doing is just pulling what's inside the sum out, and I'm just taking the first term. And here I've got r star, which this is a sphere, so it's the radius of the sphere divided by, well, any spot inside the sphere, right, that I'm interested in finding the temperature, that's r, and then r naught is the outer radius of the sphere, right? So at the sphere center, that's 0, right? And we're going to do the same thing we did before. We're going to find the temperature at the center, and then we're going to multiply by this shape factor to find the temperature at any spot inside the sphere r star. Okay, so we're going to do the same thing we did before, noting that at r star equals 0, we can plug that in here. And Houston, we have a problem. We're dividing by 0. Sine of 0 divided by 0. Oh no, that might explode. Happily, it doesn't. If you recall back to your calculus or maybe even pre-calculus class when we talked about limits, this is one of those classic. I think this one is solved by what is it called? The squeeze formula, squeeze factor. But it turns out that the limit of sine x over x as x equals 0 is just 1, right? So just like before, right, where we had this Bessel function of 0 equals 1, and we had cosine of 0 equals 1, happily sine 0 over 0 is just 1, right? And so the center line just becomes this equation. And now you've seen this 3 times, right? It's the same equation that we had here for a cylinder, and it's the same equation that we had here for a plane wall, right? So again, like this feels really like daunting and complicated, but the solution pathway is the same every time, regardless of the geometry, and everything just collapses onto itself, right? So how would you do a attempt to find a temperature of any spot inside a sphere at any time? Well, you find the Biot number, right? And that's how we get here to begin with, because if the Biot number lets us do lump capacitance, we want to do that. But if it doesn't, then we're here. We check to make sure that the Fourier number is greater than 0.2, which it will be in most cases. We then take our Biot number that we solve for in the first step, whatever it is, maybe 0.5, and we come over here and we read off zeta 1 and C1 for that Biot number. We plug in here and we get the dimensionless temperature at the center of the sphere. And then, and then we multiply by the shape factor, which has r star in it, right? So r star is the spatial location that we're specifically interested in inside the sphere. And that gives us the temperature at that particular spot for that particular Fourier number, right? All enabled by, if we go all the way back, too far, to this implication, Within one term approximation, all spatial locations exhibit the same exponential time dependence. Only the spatial multiplier or the shape function differs, right? So all of this is enabled by this implication that once you've got this guy solved, you just have to multiply by the shape function, and that gives you, from the center line temperature, the temperature at any time at any other spot inside a plane, inside a cylinder, or inside a sphere. Wow. Sphere. Okay. Whew. So we've got the temperature field inside a sphere now, right? For any time, for any location inside the sphere. Last thing we need to do is figure out what the heat is that the sphere either absorbs or gives off, depending on whether it's heating or cooling. Same game as before. We do our first law energy balance around our sphere. And then we go all the way through to find Q. We want to non-dimensionalize Q by the total amount of energy that could be absorbed by the sphere if it sat and soaked for an infinite amount of time. And that's this ratio. We go through, and the math is exactly the same. The only thing that differs is that theta star is this with this sign ratio, as opposed to whatever it was for a cylinder, whatever it was for a plane wall. We do the integration, and out pops this guy. And we recognize that this thing here on the inside is just theta star. So we can write it this way if we're interested in solving this heat in terms of a Fourier number, or we can write it this way if we're interested in solving for this heat in terms of the temperature at the spot that we're interested in. Sorry, at the center line temperature, right? Yeah, because this is this. Yeah, center line temperature. Yep. And then if you want to find the actual heat, you just calculate the total amount of heat, Q naught, multiply this whole thing by that Q naught, and that gets you Q, right? Same as we did before. And just like before, this is the exact same plot, right? But now it's applied to a sphere instead of a cylinder or a plane wall. We're ultimately trying to solve for theta star. We solve for theta star at x equals 0, which is this plot, using the Fourier number, the Biot number, to get the mid-plane temperature. And then from the mid-plane temperature, we can either multiply by the shape factor, or we can just go here and multiply by x over, I bet it is x over L. I'm going to check that. But x over L, I think by x over L, they mean R naught over L, but I think the publisher just got lazy and published the same plot 3 times, but I'll check on that. Right, to get the temperature at any location, X or R. And then if you want to find the heat, same story as before, right? It's the same plot. You take Biot number squared times Fourier number, figure out where that line crosses the Biot number line, and then you read over, and that gets you Q over Q naught, and then you can calculate Q naught and find Q, right? So same as before. Whew. Okay. So that is basically the overview for how you find the temperature for any location and any time in a transient one-dimensional conduction problem that involves a plane wall, a cylinder, or a sphere. Now, you might run into a situation where 2-dimensional and 3-dimensional effects are significant. So, for example, a cylinder that's not an infinite cylinder, in which case solutions to multidimensional geometries can be obtained from products of one-dimensional analytical results. So this actually is mind-blowing and deserves a little exploding head, which I will add to the slides before I publish them to you guys. What this basically says is you can take all of the analysis that we did before, and if you just take the solutions for those simple geometries, the cylinder, the plane wall, the sphere, multiply the solutions together, you actually get solutions for more complicated shapes. And why is that true? Well, if you go all the way back to when the original equation was solved, remember it was solved by separation of variables. It's basically a differential equation, right? And you can add solutions to differential equations, right? And get the more complicated solutions, right? The homogeneous and non-homogeneous solutions. If you follow logically all the way through, all the math all the way through, this multiplying of temperature solutions, dimensionless temperature solutions, is like adding those differential equation solutions to each other, right? So it's mathematically identical. That's why this works. So we're going to consider, just as a quick example, a short cylinder initially at uniform temperature that gets immersed in a fluid of T infinity. This is a short cylinder, so its length and diameter are comparable. This does not meet the L over R is greater than 10. This is an L over R is less than 10. And so this is not an infinite cylinder, so we cannot use the infinite cylinder solution that I just described before. And you can sort of see it visually, right? The heat transfer here is significant in both the R direction, right? So the radial direction and the X direction. And I will point out the book uses, for this example, what we would call the Z direction, the book calls the X direction, right? So X coordinate is the axial direction in this case. But look at what's happening, right? This is a short enough cylinder that once you immerse it in this fluid, it's getting heat transfer both in the radial direction. You probably can't see. There we go. Okay. Ha. Sorry. I forgot that I turned the slides off and turned them back on. You probably couldn't see what I was pointing at. Okay. So we get heat transfer both in the radial direction and in the axial direction, right? So it's two-dimensional heat transfer. The heat equation has both the X direction, the axial direction, and the radial direction in it. And then here's the time-dependent term. And separation of variables will give solutions of the form T as a function of Rx and T, right? So here's the radial direction, the radial spatial direction, the axial spatial direction, and then the time dimension, minus T infinity divided by the initial temperature minus the ambient temperature. And that equals the plane wall solution multiplied by the infinite cylinder solution, right? So the plane wall, so you can actually see it here, right? The plane wall turned 90 degrees to give the thickness of the plane wall in the axial direction of the cylinder, and then to give the radial direction in the radial direction of the cylinder, right? So you just solve these two simpler expressions, right? These two simpler problems, determine what the temperature is for the plane wall at that spot in X, determine what the temperature is for the cylinder at that spot in R, and then just multiply these dimensionless temperatures together. And that gives you the temperature for the spot in your short cylinder, right? This is mind-blowing how powerful this is. This actually makes me question why anybody would bother doing FEA anymore, because the exact solution, or at least an approximation, a very good approximation of the exact solution, is available to you just through closed form analytical solution, closed form analytical technique. Okay, so you can see here, I say analytical solutions, the multidimensional effects. The key conclusion is that 2D and 3D solutions expressed or can be expressed as products of known solutions for 1D geometries. You can do this for the exact solutions, right? For those infinite series, if you want to. It's a lot of work. But for a number greater than, this should say 0.2. Let me change that. These solutions are given by just the one-term approximations, right? Which we just walked through how to do that, right? So this to me is like mind-blowing how powerful this is. So all you need to do is figure out the solutions for the equivalent semi-infinite solid, plane wall, or infinite cylinder. I should mention semi-infinite solid is the next section that we're going to talk about in the next lecture. So we'll figure out how to do this one later. But you already know how to do a plane wall and infinite cylinder. And then this plot just shows the various X and R values for semi-infinite solid, plane wall, and infinite cylinder, so that you know when you're creating a semi-infinite plane, infinite rectangular bar, semi-infinite cylinder, or these shapes down here, like where you're counting X and R from. And the reason that this is important and this chart is given is because for a semi-infinite solid, X starts at the outer edge and goes inwards. And for a plane wall and for a cylinder, X and Z start at the center and go outwards, right? So just important to keep that in mind as you're solving for this X for semi-infinite solid versus this X for a plane wall. They might not necessarily be the same spot, right? Because one goes inwards and the other goes outwards. So just pointing that out. Okay. So as an example, if you wanted to determine the transient three-dimensional temperature distribution in a rectangular parallel pipette, which is this shape that I'm showing here, it's just the product of three one-dimensional solutions for plane walls that are that have thickness of 2L1, 2L2, and 2L3 in the X direction, the Y direction, the Z direction. So you're going to find the temperature as a function of X1, X2, and this should say X3, and time by just taking the solutions for plane wall in X1, plane wall in X2, plane wall in X3 for those particular times. Multiply them together, and that gets you the temperature at any spot inside this object for any time inside this object. And this, by the way, just so you see it again, is the expression for the temperature profile inside a plane wall, right? It's just theta. It turns out, I won't do it for you, but it turns out that the thermal energy Q that gets transferred to or from a solid like this during multidimensional transient conduction can be determined just by combining the one-dimensional results the same way that we did like for this, right? So you just find the Q value for each one of those shapes individually, and then you just combine them together, right? And that gets you Q. Okay. Whoa, that was awesome. Let's do some examples. Okay, so example one. We're annealing. So in annealing, steel is heated, then cooled to make it less brittle. So we're going to consider heating a 0.096 meter thick steel plate. Let me just make sure I add the word steel in there. These are the density specific or the heat capacity, specific heat and the thermal conductivity for steel. It's initially at a uniform temperature of 473 Kelvin, all uniform in temperature. And to anneal, steel as a material has to be heated to a minimum temperature of 823 Kelvin. So the heating is going to occur in a furnace that is at an ambient, or I shouldn't say ambient, but a background temperature of 1073 Kelvin, and maintains a convection coefficient of 250 watts per meter squared Kelvin on both surfaces of the plate. So the question is, how long should the plate be left in the furnace? And what is the plate's specific heat absorption at that time? So we know that the plate needs to be kept in the furnace at least long enough for the center line temperature, the midline temperature, to reach this annealing temperature of 823.15 Kelvin, right? So that's basically what we're going to do is we're going to say, okay, how long does it take the center line of this plate to get to this temperature, given this initial temperature and this set of conditions and material properties? Okay, so we're going to assume 1D conduction through the thickness of the plate, right? It's very long to the left and the right of the page and very long into and out of the page. So 1D conduction in the up and down direction, thickness direction. We're going to assume that the properties are constant despite the fact that the plate is changing in temperature. And this is a big furnace, right? So there's probably a lot of radiation because it's hot. And we're going to neglect radiation and just worry about heat transfer through convection. Okay, so the first thing that we do, the first thing that we always do when we're dealing with transient problems is find the Biot number. So Biot number is HLC over K. H is 250. LC is the characteristic thickness, right? So we were given 0.096 meters thick. That's the total thickness. So the characteristic thickness for a plane, for a plate is half that. I'm noticing I stole this image from the textbook, and this number doesn't match this number. We'll use this number to solve. I'll fix that too when I publish this. Um, okay. And K is given, yeah, there. K is given for steel. Okay. So 0.25. Oh man, that means it's bigger than 0.1. 0.1 is our BO number threshold for lumped capacitance. We cannot apply lumped capacitance. This is a situation where there will be a non-uniform temperature profile supported internally within this plate. The temperature lag is most extreme along the center line. So it's that location that has to reach 823 for the plate to fully anneal all the way through. We are going to assume that the Fourier number is greater than 0.2, which allows us to make the one-term approximation. But we have to confirm that this assumption is right as the last step, right? You can't just assume this, solve the problem, and then move on without proving that this is right for the temperatures that you find. Okay, so just remind myself to change this L to 0.48. Okay, so we're looking for the centerline temperature. This is the equation for the centerline temperature, right? Here's the dimensionless temperature ratio. Here's that kind of standard exponential term. We're going to flip this around because we're interested in finding the time, right? Our goal is how long should the plate be left in the furnace? So we want to find the time. Fourier number is a dimensionless time. So we're converting this around just algebraically until we get Fourier number all by itself. And then we are plugging in values to actually get the value for Fourier number. How did I know what to plug in for zeta 1 and C1, right? Because here's C1 plugged in, and then here's zeta 1 plugged in. Well, I've got a plane wall. I know my BO number, right? I calculated in the previous step, 0.25, right? 0.25. And I can just go to this chart given in the book for a plane wall and look up zeta 1 and C1, right? So that's where this value and this value come from. It's just from the chart. Okay, so let me do a sanity check here because my Fourier number for this configuration is 3.96. I want to compare that to 0.2. It's bigger than 0.2. And so this allows me to use the one-term approximation. I basically shown that it takes a long enough time for the temperature to propagate into the steel plate here to get to the midline. It takes long enough that the Fourier number is bigger than 0.2, and that allows the one-term approximation to be valid because all the higher order terms are so tiny relative to that first term that they're insignificant, they go away, right? So, okay, one-term approximation valid. And now I've got the Fourier number. I just need to take the information given in the problem and back out what the time is, right? So remember that Fourier number is thermal diffusion times time divided by L squared. So I'm just rearranging this to solve for, it's weird. Why did I do that? Well, oh, I know what I did. Okay. This shouldn't be there, right? I copy pasted this. So it should just say time is equal to rho C L squared times Fourier number over K. So I'm just going to write down to check on that. Okay, and then I'm going to plug in my values for density CL squared, right? There it is, Fourier number in K, and that gets me time, and I get 818.8 seconds, right? Which this checks with both what the book says and what AI says, so that's good. The second part, if we remember, was what is the plate specific heat absorption at that time? Specific heat absorption means energy per mass, right? Specific energy is energy per mass. So I'm going to find the amount of heat that was absorbed, and then I'm going to make sure that it's in units of kilojoules per kilogram, right? Specific energy. So I know my expression for the dimensionless heat. I also know if I let an infinite amount of time lapse that Q naught, right? My non-dimensionalizing denominator is just going to be rho CV t minus t initial minus t infinity. So, and I know zeta, right? And I know theta star at the midpoint because I just found that in the previous part, right? It's this right here, right? This. So I'm just going to plug those values in and I'm going to solve for Q. Now, notice the thing that happens here. I've got, just make sure. Yeah. Okay. So I'm looking for energy per unit mass, and the mass is the density times the volume, right? Density times volume. So normally, when I take this guy and multiply it here, I would end up with this theta star has um, density and volume in it. But the density and volume comes out from here and ends up in the denominator here, so that I have now units of specific energy. So that's how I get to the right units. It turns out, right, this is actually why this problem is framed this way. If you look at the way the problem is given, we don't actually know how long or how wide this plate is. We just know how thick it is. And so we don't actually know its volume. And so if we were asked for just the total heat, we wouldn't be able to calculate it without knowing the volume or knowing the mass of the plate. So without that information given, the best we can do is just the specific energy that gets absorbed. Anyway, so here I am plugging in the numbers, plugging, and out pops 197.7 kilojoules per kilogram. Okay, cool. And that checks with the book and with AI. So we got that. Okay. Let's do one more example. So we just did a plain wall example. Now we're going to do a cylinder example. So we have a long 60 millimeter diameter rod. Properties are given. 8,000 kilograms per meter cubed is the density. Specific heat capacity, 500 joules per kilogram Kelvin. Thermal conductivity, 50 watts per meter squared Kelvin. Is initially at uniform temperature and is heated in a forced convection. We're given a forced convection coefficient of 1,000 watts per meter squared Kelvin. So forced convection furnace maintained a background temperature of 750 Kelvin. And then we're asked, what is the rod's centerline temperature when its surface temperature reaches 750? Oh, that's not right. Okay. This should be 550 Kelvin. Ugh. That's what happens when I stay up too late. I make lots of mistakes. Yeah, this should be 550 Kelvin, right? We actually see it later on, right? When I plug in the values, right? Yeah, there it is, 550 Kelvin, right? And you can actually see it here in the problem, 550 Kelvin. Okay, so we'll change that when I publish this. What's the highest allowable initial rod temperature for which the problem is solvable? Okay, so we need first the rod's center line temperature when its surface temperature reaches this, and then we need but 550, and then we need highest allowable initial rod temperature for which the problem is solvable. Okay, so a couple of assumptions. 1D radial conduction throughout the rod and constant properties despite the fact that the temperature is changing. For a rod, or cylinder, the characteristic length is the radius of the rod. Okay, so the first thing that we're going to do, which is the first thing we always do when solving any sort of transient conduction problem, is to find the BO number. So here I am putting in my H and my LC and my K, right? So the H is here. The LC is half of the diameter, which is the radius, and then the K is given there. And I get 0.6, which, oh, darn, is greater than 0.1. So I cannot apply lumped capacitance, right? Because the BO number is too big. And so what that means is I have to use the exact solution, but I want to try to use the long-term approximation to the exact solution. So I'm going to do the same thing I did before, which is to assume that the Fourier number is greater than 0.2, allowing me to use the one-term approximation, but then I have to confirm in the end that I can do that. Okay, so at the center line, R star is 0, right? Because R is 0. And then at the surface, R is R naught, right? So R star is 1. So at the center line, R star is 0. At the surface, R star is 1. And now here is my one-term approximation for cylindrical coordinates. And so I am going to plug in, okay, I'm going to plug in, what am I doing here? Okay. I got it. I'm doing these both in parallel. Okay, so I'm doing them both. So the challenge with this, let me just articulate why I'm struggling. The challenge with this is that you don't actually know the initial temperature, right? So there's a value that you would normally be given, which they don't give you, the initial temperature of the rod. And so we're going to end up having to solve this like two equations and two unknowns. So that's what I'm doing here. I'm basically setting up these two equations, and I'm going to solve one, and then I'm going to get the answer and plug it into the other. So this version of the equation is for the edge, right? So at R star equals 1, the outer edge, and then this one is for the center line, R star equals 0. Okay, and then the only thing really that changes though, right? The zetas are the same. The only thing that changes is R star is 1 here and it's 0 here. So the Bessel function is going to be Bessel function 0th order of zeta 1. And over here, it's just going to be Bessel function of 0. Okay, so we'll see that on the next slide. Okay, so this is what I'm interested in solving for, right? The center line temperature when the temperature here reaches 550 Kelvin. So I've got this kind of highlighted in blue so that you can keep track of what I'm trying to solve for. The thing that makes this problem hard, I don't know T initial, right? So I've got that in red to remind me that I don't know it. And what I need is the Fourier number, right? So I need to know the time um, that it takes to get to here. Okay, so these are my two equations, right? And there's actually at the moment three unknowns, but that's okay. So three unknowns. So let me just plug in and get my values for the Bessel function, and then we'll go from there. So for an infinite cylinder, which this is, I know my BO number, 0.6. And so I can determine zeta 1, right, which is 1.0184. And I can determine C1, which is 1.1345, right? So that's where those are, where those come from, right? So that's like this value and this value or this value, that's where those come from. And then knowing um, that R star equals 0 here and 1 here, I can figure out what the Bessel function is. So for this one, it's just 1, right? That's the center line temperature. So just 1. And then here, it's zeta times 1. Let's see. Why did I do that? Zeta times 1. Huh, okay. I've got this highlighted, and I think maybe I don't need that highlighted because I actually do it better down here. Okay, so you can see here, zeta 1 is equal to 0.0184, right? So that's this one. Bessel function of the 0th kind of 0 is 1. That's this one. Okay. So this is what I was looking for. So Bessel function of the 0th order, 0th kind of zeta 1, right, which is here, but multiplied by 1, right? So it's just that value, is approximately 0.7652, right? Okay. So it's there, 0.752. How did I get that? Well, I've got okay. I just figured it out. I just figured out what I did. Okay. I was like, what? So here's my confusion, right? Why in the heck have I got 1 here, right? When the number that I'm looking for is 1.0184. Well, okay, fine. This is tabulated data, right? There's an actual Bessel function of the 0th kind sitting here for a zeta value of 1.0184, right, which is the value that gets plugged in right here. but everything's tabulated, right? So I could, if I wanted to, like interpolate to get to that. But my God, 0.0184 is really close to 1.0, right? 1.0184 is really close to 1.0. So okay, so now I remember what I did, which is I just took this value, and that's what this approximation is, right? It's like it's awfully close because this value is awfully close to one, right? So that's where this comes from. I also plugged it into AI and I said, hey, AI, what is the Bessel function of the zeroth kind or zeroth order for a zeta of 1.0184? And out popped the actual exact value, which is 0.7570, right? Okay. So, and I could, right, just take like in Excel, for example, you can plug in, I showed you that before, like values for Bessel functions, and out it would have come. So I could have gotten this from Excel as well if I wanted to, but I got it through AI. Okay, and C1 is just that value. Okay, okay, whew, I'm caught up now. So now I've got everything figured out. I've got everything figured out. I've got all my numbers, so I can plug in my numbers here. Except I still have this challenge, which is I don't know the initial temperature, right? So I still have one equation with multiple unknowns, right? So even though I've got all these numbers pinned down, I know C1, I know zeta, I know the Bessel function of zeta, and so forth. I've got this challenge, right? Which is I don't know enough to solve this. Okay, here's the trick, which is um, this guy equals the center line temperature, and the center line temperature, remember, is just um, it's just this, right? So I could say that this is equal to this because this is equal to this is equal to this, right? And so when I set them equal to each other, it turns out just by great good fortune that this term in the denominator, which absolutely cannot be zero because it's the initial temperature minus the ambient temperature, and this cylinder is at a different temperature than the ambient temperature in the furnace. So this can't be zero. So I can divide both sides of the equation by that, and that eliminates one of my unknowns, right? And so that's the way around that problem. So now I have one equation with one unknown. Previously, I had one equation, two unknowns, but that unknown went away when I set this equal to this because this guy equals this, which is the expression for the center line temperature. Whoa, okay. So now I can find the center temperature, um, which is this equation, and I know everything to plug in. And so that gets us to the next slide, which is here, right? So that's that same equation from before. This is me just pulling all those same constants that I found from the previous slide so I can plug them in. So here I am solving, right? So plugging in ambient temperature, plugging in the Bessel function, zeroth order Bessel function for zeta equals to 1 point. Well, I actually plugged in 1, right? Um, and then here's that temperature difference, right? So the temperature at the outer edge, which I know 550 minus the ambient temperature 750, and then a Bessel function of the zeroth kind, but 0 is 1, so that gets multiplied by 1. Okay, so I get 488.6 Kelvin. Notice I did this 2 times, right? I did it once for my approximation, right? So this is me approximating uh, this Bessel function using zeta equals 1 when zeta was actually 1.0184. And then here is me doing it for the exact value of that Bessel function that I got from plugging in the exact value of zeta into AI, or you could do it in Excel, right? And getting that value. Right. So this is like the analog version. This is the digital version. And you can see, right, my approximation was not very bad. They're only off by about 3 degrees Kelvin. So I get 485. 0.8 Kelvin, right? And so it's actually this value, the lower value, which is the one that checks with the book, and that checks with AI. But this is my version of it, again, using a slightly different value of that Bessel function because I did not know from the table zeta 1. I knew something close to zeta 1, but I didn't know zeta 1 exactly, right? So that's why I get two different answers. Okay, so we still don't know, and there is actually no way of knowing the initial temperature of the rod as it's getting put into the furnace. But we still have this burden of confirming that the Fourier number is bigger than 1. I'm sorry, bigger than 0.2 to ensure that the assumption that underpins all of this, which is that I can use the one-term approximation, is valid. And so that actually gets us to the second part of the problem, which is what is the highest allowable initial rod temperature for which the problem is solvable using the one-term approximation. So the way that I'm going to do that is I'm going to say, okay, I can solve using the one-term approximation all the way up until a Fourier number of about 0.2. So I'm going to plug in a Fourier number of 0.2 and calculate what that initial temperature is for this Fourier number, right? It's basically I'm finding out the amount of time that it takes for the center line of the rod to increase up until it reaches this temperature from some initial temperature. What is that initial temperature? If the Fourier number is too small, right, this process happens too fast, I can't use the one-term approximation. So what I'm actually checking or looking for is a maximum temperature, right? If I get temperatures too close to 485, the heating process happens too fast, right? There isn't enough time, and the Fourier number is too small, and I can't use the one-term approximation. So what I'm looking for is an upper bound on the temperature of the rod when I put it into the furnace. Okay, so here is the expression for the oh, okay. So this is just the one-term approximation, right? And then here I'm solving for the temperature at the outside edge, right? That's a value that I know, right? So, and I'm basically putting in the appropriate value for n and for r star, right? So here's r star for the edge, and then I'm gonna turn this around and solve this for the initial temperature. Oh yeah, okay. I was like, where did I get the Fourier number from? I get the Fourier number from here, right? I've already said it, 0.2. Okay, so here I am doing it, right? So here's 750 plus here's that 550 edge temperature minus 750 furnace temperature. Here's C1, which I got from the table before. Here's here's zeta, minus zeta squared, right? Zeta is the zeta value that I got from the table. Here's where the Fourier number comes in, 0.2. I plug that in. And then here is my Bessel function, zeroth kind for zeta 1. I'm going to use my version of the solution, right? The one that I like from the table, which isn't quite right, but the analog version. And what I end up with is 466.5 Kelvin. So what that means is that if the rod is colder than 466.5 Kelvin, I can use the one-term approximation, and everything that I did before is valid, right? So you don't actually know what the initial temperature is, but if it's colder than this, then we're good to go, right? And so that's why that second part of the question is posed the way that it is, to basically tell you like the temperature bound at which you can no longer use the one-term approximation. Whew. Okay. that was a lot. All right. That brings us to the end of this lecture. Thanks for your time and attention. And I will see you in the next one.